Here's my HP 64,000 emulation system. It's set up right now with a 6809 Motorola 6809 emulator. This is how development would have been done in the 80s for embedded systems, likely with the 6809 microprocessor. I picked this up last year, had to rebuild the floppy drives, and I went ahead and added the PROM programmer card, and I've got a couple different PROM programmer units. Originally it had this blank that went over that. Anyway, I recently got it working, and I'm actually able to emulate 6809, and as well as emulate memory, as I'll show you here. So before I boot it up, went ahead and on a Windows 2000 computer I got running here, I'm running HP drive to emulate an HP 7914 hard disk, about 128 megabytes, and through a GPIB card and a GPIB cable connected to the back of the 64,000's HPIB connector. The 64,000 believes that this is a hard drive unit here. So I'll go ahead and fire it up. Okay, and it's only showing one local disk drive. I have this one disconnected because it runs both motors when even just one drive is being accessed. In this one, I need to tear it apart again and lubricate part of the spindle because it's really noisy. So, okay, so it booted because that drive was available for it. Otherwise, it would just say, it would throw an error and I'd have to boot it with a floppy disk. So first thing let's do is date and time. Let's see, format. Let's do 13 June 2022. Oops. Right. Okay. Got our date and time put in. Signing in as a user. Okay, there's our user ID. So let's make a new assembler file. But I have one already I called test, so I don't have to type it out for this. So let me just, we'll save it into a new file. We'll call test2. Okay, so I can scroll up and down here. I'm missing a key. Fortunately, I still have access to the stem, so I can use it. So here's our assembler file. We referenced that we're doing the 6809 architecture. So the code's going to begin in FFE0 because I wanted it to. We're just going to do 3 no ops and then a jump back up to the top. It's going to loop that. This code down here at the bottom is because I put this in the reset vector area. So if execution behaved like a proper 6809, it would begin with doing a jump from whatever's stored at this address, FFFE, and FFFF, which was the FFE0, which is, it looks like it's big endian here. I wrote this quite a while ago, so I'm kind of relearning it on the fly here. Okay, so let's go ahead and end this. let's assemble test 2 options. Let's do list, expand, extra ref. So we get the cross references. Not that there are anything like that. Okay, it says errors 0. Okay, so let's do it again. Put it on the display. So now we can see it as it happens. Okay. Looks like I can't scroll through it, but you can see it. Fortunately, the code was small enough you can see that. So here's our code. Here's what it assembled it into. Hex 12 is the no-op instruction, and then it does a jump back to FFE0. It does that in a loop. All right, very, very simple program, and it's assembled into a file. In fact, if you want to see see if we can list. Okay, so our source, that's what we originally used the editor to create, and then when we assembled it, we created the assembler sim file and a relocatable file. So then next we'll use the linker to link it. Let's see. I don't really think I need to do any of these, but I'm gonna go ahead and do it anyway. Link. Oh, right. First I need to do link test2. Link test2 list file display. How about just link? Okay, object. Here we go. This is where we're doing object files. Test2, and it's a link sim file. No, it's not. Clear that. Okay, there are no library files. Yep, can all begin at 0. See list on xref. Let's go ahead and turn that on as well. That's all good. Absolute file name, test2. Okay, they believe it linked it. Yep, errors 0. Let's go ahead and display now we have link sim and link com files, and as well as, here we go, our absolute file. That is our binary program. So next we can go to the emulate. Start a new one here. We're going to do the internal clock source because here's the pod connector for the 6809. Typically you would plug this into whatever system you're developing for, your target system, in place of the CPU. You'd pull it out, or maybe you don't have a CPU yet, you'd plug this in and develop around it. So it's possible that in your own circuit you could have your own clock source. Well, in this case, we're just gonna, because we're not gonna connect this to anything, we need this to have its own internal clock. So that's what we're gonna use. Restrict to real-time runs. We're going to say no because we want to be able to step through code. We can go ahead and break on illegal opcode. That's fine. Okay. Okay, so this is our emulation memory configuration. So the emulation system needs to know what type of memory you have where, either in your what they call user memory, which would be the device you're developing for, your embedded system would have memory potentially, or I/O or ROM. We're not going to have any. So I'm going to go ahead and just assign all of the available emulation memory, which is just RAM that this system has built in for the emulation process. I'm going to go ahead and assign all 64K of that to the 6809 address space. So, which the 6809 can only address 64K of addresses, so the entire address space is going to be used up for it, just for this test. So let's do address 0 through 0FFFH will be emulation. Let's do RAM. It really wouldn't matter because this code doesn't attempt to modify anything, and the only difference between these two in terms of the emulation memory on this is if you assign a block, you can assign these in blocks. We're just assigning all of it at once, but you can assign a block as ROM, and the only behavior that it has that's different from assigning it to RAM is that if your code attempts to write to that area, it'll break and throw an error so that you're aware that your code tried to write to ROM, which of course you can't do that. We'll throw in the note that it's also possible to tell the system that a specific address or addresses in your ROM space are actually okay to write to. Not that you will successfully write to it, but maybe you use that for writing to a register. It picks that up and uses it for bank switching. So it allows you to do that as well. So assign it as RAM. We don't need to worry about overlay. Okay, so, oh, I screwed that up. We're doing 0 through 0FFFH. There we go, that's our 64K. Oh, crap. Try this again. Okay. All 64K is assigned. And we're not going to use simulated I/O, which is a really cool feature of the 64000 system, allowing you to pass either the keyboard or the display, or I guess not this disk, it'd be that disk, files, or the serial connector on the back of this. Pass that through to your system that you're developing for, so that you could write code that for this system that would write or read files, or can use your keyboard interface to send inputs to it. So it's kind of neat. We're not going to do that here, so no. Nope. We're going to call this command file test2, so we don't have to do this whole process again. If I wanted to open this up, I would just open this command file that we just created through this series of prompts. Okay, 6809 it's waiting. So let's do run from, so the address FFE0 is where we started, right? And we're not going to run until, we're just going to run. Uh-oh, maybe I had us run from the wrong location. So let's go take, I don't actually remember. I guess it's not FFE0. Let me look at display, memory, mnemonic. So this is kind of like a disassembler view. So let's come back here and look. Looking for that jump code. Something is wrong. Okay, I realized what I did wrong here. I never loaded our absolute file into memory. So this is just garbage. We've been trying to execute garbage. So I need to load. Okay, now if I display memory mnemonic, here we go. Okay, doesn't show FFE0, and I can only assume that has to do with the fact that this this one above it, yeah, here it is, 12H. That's our first no op. It belongs down here. Okay, so the garbage in memory above FFDF. This instruction uses the next byte in memory as data. So it's using 12H is the data for this instruction. So that's not actually correct. What we're going to do, run from FF. That's not a 0. That is an O. Here we go. Okay, now it's running, and it hasn't broken yet, so it's stuck in a loop. That's a good thing. That's what we wrote. So let's display registers. I don't think we're going to see anything interesting because it's just no ops and jumps. So anyway, what if we break and then perform this step? Here we go. So we're at FFE2. So the next one should be a jump instruction back to FFE0, and took the jump. Now it's executing no op, no op, no op, jump. Here we go. That proves it. The emulation system is operating. I guess next I'll have to try to develop some sort of 6809 based system with this guy, just to prove it out.